Hey everyone, today we're looking at different characteristics of a function such as increasing and decreasing intervals. We're also talking about domain and range by looking at its graph, and then even in odd functions, how we classify them as well. So those are the topics we're looking at. Here they're saying using a graphic calculator. I've already done that and sketched it out. You can see that this is our absolute value function, and if you think back to when we were transforming these by hand, we looked at the h and the k as a way of showing how it was moving. So 4 to the right and 2 up places it here. So now that we know that it looks like, let's identify the domain and the range. And then we'll add on one extra question. Let's evaluate the function with an input of 0. So the domain, again, is all of your inputs, all of your x coordinates. And you can see you have a negative x, you have a positive x, you have an x of 0. There's no gaps or holes. It's all real numbers. We're using interval notation here. The range is describing our outputs, our y-coordinates. You can see we have a y-coordinate of 2, and they increase from there. So square bracket on the 2, meaning we're including the 2 as well, all the way up to infinity. So if we evaluate the function with an input of 0, that means plug in 0. So absolute value of 0 minus 4 with the plus 2 will give us a result of 6. So there's your output of 6. So we know this point right there is 0, 6. Here's number 2. Again, I went ahead and showed you what that would look like. That's the top half of our circle with a radius of 3. Be careful here. Don't try to simplify this. You cannot take the square root and cancel out the power of 2 because these are separate terms. In the same way you cannot take the square root of 9. So that's what you type in and we get this. So let's talk about our domain. Our domain is from negative 3 to positive 3. I need a square bracket on that because we are including those values. Our range is from 0 up to 3. So we're talking about the y-coordinate starting at 0 and increasing towards 3. And if we were to evaluate the function at 0, when the x-coordinate is 0, the y-coordinate is 3. So there's your output. Here's another illustration. There's no breaks, no gaps. Our domain is all real numbers. And our range is also the same. All right, think about this one here now. On this side of the graph, we have a termination point that's at 3, 1, and on this side, negative infinity, positive infinity would approach that eventually. So our domain is thinking about those x-coordinates, and we have an x-coordinate of negative infinity, we have an x-coordinate of 3, and we want to write that in that order from smallest to biggest. And then the range, think about the y-coordinates. We have a y-coordinate of infinity, we have a y-coordinate of 1. Again, we want to order that from smallest to biggest. So the interval is from 1 to infinity. All right. You may remember something about the vertical line test. That's a common topic in algebra classes where we could take the visual image and just give it a quick vertical line. And we're asking the question, how many points of intersection are there when that line is touching the graph of our function? And if the answer is exactly 1, that means there's 1 input and exactly 1 output. It is a function. However, if you give it a vertical line test and you can find a spot where the vertical line touches the graph in more than 1 point of intersection, that means you have 1 input but you have 2 outputs. You have 2 y-coordinates here on the circle. So that is not a function. So that's a pretty quick and easy way to determine visually if it's a function or not. Here we have an interesting shape. That's a vertical line. So if you give that the vertical line test, how many points of intersection do you get? So many you can't even count, right? There's an infinite number, so clearly not a function. Number 8 is hard to see there. I'm going to zoom in and kind of redraw it. What we're looking at is what we call a step function because it steps. In this case, it steps downwards, where you have this closed circle on the left of each segment and then the open circle on the right. So let's talk about giving it the vertical line test. If you give it the vertical line test on the leftmost of the segment, you can see there's exactly 1 point of intersection. If you give the vertical line test in the middle of the segment, again, exactly 1 point of intersection. So what happens here on the right side of the segment? We're going through the open circle and we're going through the closed circle. Is that 1 or is that 2 points of intersection? That's only 1. Because the closed circle means that I have a point here, and the open circle means that I do not have a point here, so I'm not passing through a second point. So this is a function, and that's why we call it a step function. We're talking about these characteristics of increasing and decreasing intervals, or even constant intervals. Notice that we're always reading the graph from left to right. And if the height is falling, well, it's decreasing. If the height is staying the same, it's constant. And if the height is increasing, then the graph is increasing as well. There's the technical description using function notation. Let's just go right to our examples on the next page, and we'll take a look at these intervals as well. So here it says use your graphing calculator. I'm going to just go ahead and show you what we would look at here on number 9. We would actually have two separate branches facing outwards. So we want to know what these points are, and again, if we take a closer look at what our scale is and what the graphing calculator tells us, this point is at -1, 0. This point is at +1, 0. But it is also helpful to describe the endpoints of those two branches. So on the left-hand side here, this would be -∞, +∞. So as the x-coordinate goes increasingly leftwards, the y-coordinate is increasingly bigger. And on the right-hand side, +∞, ∞. All right. Now, when we're talking about describing these open intervals, we are describing where the interval starts and where it stops. So we are not describing the height at which it changes. So we are not looking at the y-coordinates. We're looking at where does it start and where does it stop, meaning you are only looking at the x-coordinates. So I highly recommend on these types of problems you circle or flag just the x-coordinates because that's all you're using. So we want to know where is this decreasing, where is it increasing, and where is it constant. So you can see that as you read the graph from left to right, this first branch we are decreasing in height. We're decreasing in height from where to where? From starting at -∞ all the way up to, but not including, -1. That's what this word open interval means. Open is another way of saying we are approaching, but we're not actually equaling it. So we don't use a square bracket, we use the rounded brackets instead. Here we are increasing from left to right, so where are we starting? +1, where are we going? +∞. There is no constant interval. Here in this next section, again, if I were to use my graphic calculator on that, it would give me a shape like this. So we want to know what are these turning points right here. This is located at -4, 3. I only know that because I looked at my graphing calculator to figure that out. Sorry, that's a -4, -3. And this is a -1, -3 as well. Again, take a look at the ends. We have a -∞, -∞ on the left, and on the right, +∞, -∞. Now, once you have all of those ordered pairs, circle the x-coordinates, and that's all you're allowed to use. So here's our increasing interval, here's our constant interval, and here's our decreasing interval. So we are decreasing from here to here, starting at -1 and ending at +∞. We are increasing from here to here, so -∞ to -4. So again, notice we're not describing the height at which it changes. We're not looking at the y-coordinates. We're just saying it changes in an increasing way, starting here up until this value. Constant at -4 up to -1. All right. Our final topic is even and odd functions. This is describing different types of symmetry. And we're going to be looking at this both graphically as well as algebraically. Algebraically is a bit more complicated. We'll come back to that in a moment. Let's start off with the graphical interpretation. We are either going to find a case of even or odd or neither. Those are the only three options we have. And when we're describing an even function, we're saying that it has this kind of characteristic. It is symmetrical about the y-axis. That means you should have a line of symmetry on the y-axis. So let's take a look at this first shape. Here's a parabola. Find the vertex. There's the vertex. The line of symmetry always goes through the vertex on a parabola. So there's my line of symmetry. And the question we ask is, that line of symmetry also on the y-axis? Yes, it is. That describes an even function, meaning it has a mirror image. It has a line of symmetry. It has reflection symmetry about that y-axis. Now, I know there's no numbers here, but let's just pretend that this function is described by x squared minus 2. And let's say we are going to test some inputs. So instead of using the x comma y that you see printed here, let's use 2 comma something. Let's see what that output is. So let's say that we were to input a 2. We would have a result of 2. And then on the other side, let's see what would happen if we were to have an input of negative 2. So that would be a negative 2 squared minus 2. And what we're analyzing here is we want to know, are the outputs the same or are the outputs not the same? They're obviously the same. We got the exact same output. That means the y-coordinates are the same. The outputs are the same. When you have a positive input and a negative input, but you get the same outputs, that's what's happening when we have a line of reflection about that y-axis. Now, if we have an odd function, graphically we're going to see it's symmetrical about the origin, meaning we have rotational symmetry, and that's what you see here in this instance. If we were to take a look at our tracing paper here, here's my graph. Here's that point. If we rotate this 180 degrees, you see that it maps onto itself. Well, I didn't draw that right, so there. It maps onto itself. And there's this point. So if you have 180 degrees of rotation, we call that an odd function. Now let's see what's happening if we were to plug in a positive and a negative input. So let's make up a function that could maybe represent this. Let's look at x cubed as if that were the function. What happens if you plug in a positive or a negative input? Do we get the same output like what we saw previously? So 2 cubed gives me 8, and negative 2 cubed gives me the opposite of 8. So notice that they are not the same. They differ by a sign. So one is positive, one is negative. So when you have a positive input and a negative input, and you're getting the same value but they differ by a sign, that's what we're looking for algebraically when we have rotational symmetry. For this third example, we do have a line of symmetry, but this one happens to be horizontal. So that is a neither pattern, meaning it has neither a reflection symmetry about the y-axis nor rotational symmetry. And to go even a step farther, if you're taking a look at this particular example, if you give it the vertical line test, it fails. It has 2 points of intersection, so technically this example is not a function to begin with. So if it's not a function, then we cannot even classify it as having either even or odd symmetry. So let's take a look at a couple more graphical examples, and then we'll get to the algebra examples. So going to the top of the next page, here we have number 14. We have a parabola again. First, find the vertex. There it is. That means our line of symmetry has to go through that vertex, and we ask the question, is that line of symmetry on the y-axis? No, it is not. So this is neither. It's neither even nor odd. It is not even because it is not on the y-axis. Number 15, this is just the slope of a line, -2. So that's going to be falling. It passes through the origin, so something like that. I'm trying to draw a straight line there. So it does not have a reflection about the y-axis, because if you reflected this point, it would land over there. So it does not map onto itself. But we do see that this point rotates 180 degrees and lands on the line there. So we do have rotational symmetry, so that is an odd pattern. Here in number 16, again, this is sort of this pinwheel effect. we're going to see that rotational symmetry. So again, we have an odd pattern. And here on number 17, that's my absolute value function. So find the vertex, put the line of symmetry through the vertex, and then you ask yourself, is that line of symmetry also on the y-axis? Yes, it is. So we have reflection side to side. So that's even. So that's what's happening graphically. We're really looking at these two kinds of symmetry. So the question is, can we do that without actually looking at the picture of the graph? Can we just work with the equation and algebraically determine if it shows up as even, odd, or neither? So I'm going back to the previous page to look at the summary of what we're going to do. It's the same series of steps for both of these. First, we're going to plug in negative x. We're literally plugging in the opposite input. So we're not using a number. We're using a negative sign in front of the x. We're then going to simplify, and then we're going to look at the result. The function will be even if, after we've plugged in that negative x as the input, my answer is, so check this out, that's the notation for the function, meaning if it's exactly the same output, if it's exactly the same result. That's what we were seeing down here in our first illustration. If I plug in the negative input, will I get the exact same output? That's the even pattern. Now, if it's an odd function, we're going to go through those same steps. We plug in the negative x, we simplify. The function will be odd if the result of that is, so take a look at this. You see that exact same function notation. So it's the same result, except there's a single negative in front. That's what we were seeing in this illustration in the middle. Here I'm plugging in my negative input. The result is the same output, but with a single negative in front. That's the odd pattern. So we want to see if we can find that pattern showing up in a more abstract case, not working with specific numbers, but working just with x's and the opposite of x as we plug that in. So here we are, returning back to page 7. Let's take a look at examples 18, 19, and 20. So here on number 18, we have f of x equals x to the 6th minus 2x squared plus 3. So we're going to take that function and we're going to plug in the opposite of x. That means that's my input. So wherever you see this input symbol in its place, put some parentheses there and drop in the negative x. That's step 1. Now we're going to simplify it. So anything to an even power becomes positive. So this becomes a positive x to the 6th. Here you still have that coefficient of a negative 2 in front. So we're just looking at this piece right here. What happens when you square the negative x? Well, that's a positive x squared. And then there's your plus 3. Then you ask yourself, is the result exactly the same as the original function? It is. You got your positive x to the 6th. Your middle term is the same, minus 2x squared, plus 3 at the back. It's exactly the same. That's an even function. So that's what we mean by solving it algebraically. So we're really just focusing on part A and the directions here when it says determine it algebraically. Here's number 19. So take the function and drop in the opposite input. So where it says x cubed and where it says x, set up your parentheses to drop in the opposite input in each of those places. And now we simplify. So a negative x to the power of 3 is still negative. And when you add a negative x, that's the same as subtracting an x. So we ask ourselves, is this result exactly the same as the original function? If it's the same, it would be even, like what we saw out there. But no, it's not the same. So we have a follow-up question. Can we make it the same, but with a single negative out front? Now, both of these terms are negative when originally both were positive. So I can't just say, hey, look, there's a negative out front. No, we have to look at everything else and say, is it exactly the same as the original function except for a single negative out front? And currently no, but let's factor out a negative 1. And that results now in negative times the quantity of a positive x cubed and a positive x. So now you're looking at what's in parentheses. Notice that's exactly the same as the original function. And you have a single negative sign out front. That's the pattern you're looking to determine that we have an odd function. Here in the third example, Let's plug in the opposite of x here and here. So we have the opposite of x multiplied to the square root of the opposite of x with a plus 5. There's really not much to simplify here because we don't have any exponents to consider, so it just looks pretty much the same. Does it look exactly the same as the original? If so, it would be even. No, it is not the same. Does it look exactly the same but for a single negative out front? And again, the answer is no, because we have this negative on the inside of that radical. So it's not the same. Can I factor out a negative 1? No, because these are factors and we cannot factor out a negative 1 here or here. That would make it look the same as the original. Be careful. Don't just think, hey, I'm going to just do this. We have the negative out front, but again, the inside is not the same thing. So no, that doesn't work. So this is a case of neither pattern, neither kinds of symmetry. And with that, we'll finish up here.